8.6 Solving logarithmic equations. So a logarithmic equation can be solved by expressing it in exponential form and solving for the resulting exponential equation. Okay, so we can toggle between these, and we saw that at the beginning of Unit 8. So in other words, if log base 8m equals log base 8n, we can cancel these out and m equals n. And we've seen this before. Okay, let's talk about inadmissible roots. And we started talking about this in 8.6. So what we want to do is we want to ensure to check for inadmissible roots. Okay, and just recall the domain of a logarithmic function is 0 to infinity. Okay, so 0 to infinity. Or if there is if there's a reflection in the y-axis, it would be negative infinity to 0. Okay. This right here is going to be the general form. It's going to be negative infinity to the vertical asymptote. And the vertical asymptote if there is a horizontal shift. So let's go horiz shift. Okay. Notice that these two brackets are open brackets. They're round brackets. And what that means is that we're never ever going to reach the vertical asymptote. We're going to come infinitely close to it. Okay. So it's one of two things. So this one is going to be if there is a reflection in the y-axis. Okay. So to check, what we have to do is we have to substitute each of the solutions into, it's called an argument. So if we had, like, for example, log base whatever, this right here is going to be called the argument. And each argument has to be greater than 0. Or what it's going to do is it's going to yield an undefined value because the graph is not going to be defined at that point. Okay, so let's take a look directly for example 1. Okay, solve for x and then check for inadmissible solutions. So we have log base x 0.04 equals negative 2. So what I'm going to do first is I'm going to convert this logarithmic function to an exponential function. So we have x to the negative 2 equals 0.04. Okay, so what we'd have to do to solve for x is we have to get this negative 2 out of the exponent. In order to do that, what we're going to do is raise the exponent to its reciprocal. Okay, so instead of 2, we're going to use 1/2. Also, if we have a negative in the exponent, we want to get rid of that. And don't forget, negative times the negative number is going to yield a positive number. So that exponent is going to be negative 1/2. And what we do to the left-hand side, we also do to the right-hand side. So if we were to think power of a power, and we were to multiply these, negative 2 times negative 1/2 is just 1. So that got rid of the exponent. Now we're going to have x isolated. Okay, and the 0.04 raised to the negative 1/2, I'm going to put in my calculator, and I get 5. Okay, so we don't need to check. Oh yeah, I guess we can. Let's do the check. So x equals 5. In this case, we're talking about a base. So the base number has to be greater than 0. Therefore, x equals 5 is valid. Okay, for B, we have log base 7, 3x minus 5 equals log base 7, 16. So we know that 7 to the log base 7 will cancel out. So what I'm going to do is I'm going to raise both of these to the 7. Okay, those are going to cancel, and we're going to have 3x minus 5 equals 16. Okay, it's a law that when we have a log of the same base, then we can drop those logs and equate the arguments. Okay, we've seen this before. So bring over the negative 5, we get 16 plus 5, we get 3x equals 21, and we get x equals 7. Okay, now we have to check. So in B, here's the thing. This is just a number on the right-hand side. We don't have to check that. We only have to check when we see an x in the original. So the x is in the argument. So we have to check that 3x minus 5, when we substitute in a 7, it's going to be greater than 0. So that's 21 minus 5. Is that greater than 0? Well, yes, 16 is greater than 0, so x equals 7 is valid. All right, example 2, solve and check for inadmissible solutions. So we have log base 3x equals 3 log base 3, 4. Okay, first what I'm going to do is I'm going to bring this 3 back up. So we're going to have log base 3x equals log base 3, 4 to the 3. When we have both of these as log base 3, and you can't have that coefficient there, you have to bring it up. Okay, what we can do is we can cancel those and equate the arguments. So we have x equals 4 to the exponent 3. Okay, and 4 to the exponent 3 is just 64. So what we want to do is we want to check. So going up to the original, this right here is just a number. There's no x value in it. We don't have to check the right-hand side. For the left-hand side, we have an argument of x. So we're essentially saying, like, is x greater than 0? Well, 64 is greater than 0, so this solution is valid. X equals 64. B, log x plus 3, so of course this is the base of 10, equals log base 10 of 1. So we can go ahead and cancel the log base 10s, and we can equate x plus 3 equals 1. Okay, bring over the 3, we get x equals 1 minus 3, and we get x equals negative 2. Okay, so the check, going back up to the original, log base 10 of 1 is just a number, so we don't have to check that. This is just a number. We have to check when we have an x value. So we do have to check that x plus 3 is greater than 0. Okay, let's go ahead and sub in our solution. Negative 2 plus 3 is greater than 0. 1 is definitely greater than 0. So this solution is valid. X is going to be equal to negative 2. Okay, so don't forget, just because it's negative doesn't mean it necessarily is inadmissible, because now we're not talking about log base 10x, we're talking about the situation where it moves to the left 3 units. So now we're looking at this, and at negative 2, it's like this, this graph is defined, right? Because this is x equals negative 3 to be the vertical asymptote. Okay, so you have to take into account those transformations. C, log base 2 30x minus log base 2 5 equals log base 2 12. So this is really nice because all of these have a log base 2. Okay, we can do this one of 2 ways, but I'm just going to leave each of these on their own sides of the equal sign. And I'm going to use the product law of logarithms to collect the 30x and the 5. This will be quotient. actually. So log base 2, we're going to collect the 30x by dividing it by 5. Okay, and then I'm going to equate that to this as it is, log base 212. Now I'm going to rewrite the 30x divided by 5 by doing 6x, and that's log base 212. Okay, now we have one expression on the left-hand side, one expression on the right-hand side. Both are log base 2. So let's go ahead and equate 6x equals 12. Okay, divide both sides by 6. We get 12 over 6, so x equals 2. Okay, our check for this one. Let's take a look at anywhere where x occurs in the original equation. So we only have the 30x. This is the only x. So we need to check if 30x is greater than 0 when we sub in the 2, when we sub in our solution. Okay, that's the question. So 60 is greater than 0, so this solution holds. D, log x plus log x squared equals 12. Okay, so both of these are base 10s, so let's go ahead and collect the x and the x squared. Since they're added, we're going to multiply them. Log base 10 x times x squared, and that's going to equal 12. Okay, and obviously x times x squared is just x cubed. So now we're dealing with log base 10 x cubed equals 12. So I'm going to rewrite this as 10 to the 12 equals x cubed. Okay, you can write 10 to the 12 out. It's going to be 1 followed by 12 zeros. Okay, it's too big for me. So I'm going to do this with exponent laws instead. So we have some number, 10 to the 12, doesn't matter, it's just some number, equals x cubed. So we want to get this to equal x. So let's go ahead and cube root this. You know what? Instead of writing it as a radical, I'm going to write the cube root as 1/3. This goes back to our approach where we multiplied by the reciprocal to get 1. So a number times its reciprocal, which is 1 over that number, this will always yield the answer of 1. Okay? And therefore, we have x to the 1, or x, equals. Now, this side, we're also going to raise to the 1/3. And then this is easy. 12 times 1/3, right, exponent laws, is 4. So x is going to equal 1,000. 1, 2, 3, 10,000. And I'm going to check this on my calculator. Yeah. Okay. And for the check, every single time x occurs in the original question, I'm going to check. So I'm going to check that the argument x is greater than 0. So yes, 10,000 is greater than 0. The next one is I'm going to check that x squared is greater than 0. Because there's 2 different x values in the original. So I'm going to say 10,000 squared is greater than 0. It's a number, squaring it is positive. Okay, so that solution is valid as well. Okay, example 3. Solve log base 2x plus 3 plus log base 2x minus 3 equals 4. And then check for inadmissible solutions. So because these two are the same base, we can use that product rule where we go log base 2, and then we're going to multiply x plus 3x minus 3. Okay? And then we'll just bring down this negative, or sorry, this positive 4. Okay? So I'm going to say, let's expand this. and we're going to get x squared minus 9. This is difference of squares. If you don't see that right off the bat, to expand, you go ahead and expand and simplify. Okay. Now the question is, to get rid of the log, we're going to convert this into exponential form. So 2 to the 4 equals x squared minus 9. Okay, so what is 2 to the 4? Well, it's 16 equals x squared minus 9. Let's go ahead and bring that 16 over. We get x squared minus 9 minus 16. And then that simplifies to x squared minus 25. So we have one of two ways to do this. We can either bring over the negative 25 and we can solve by square rooting, or we can factor. But because this is a functions class, I'm going to go ahead and factor. X squared minus 25 factors into difference of squares. X plus 5, x minus 5. Okay, and then we have two solutions. X equals negative 5, x equals 5. Okay. We have to check both arguments. So going back up to the original, we have to check that x plus 3 is greater than 0. We also have to check that x minus 3 is greater than 0. Here's the issue. We got 2 for each. So I'm going to split this like a T-chart. Okay, so let's go. Negative 5 plus 3 is greater than 0. Well, negative 2 is not greater than 0. So x equals negative 5 is inadmissible. Okay, we can try the other one. 5 plus 3, is that one greater than 0? Well, 8 is greater than 0, so yep, that one holds for the first argument. Remember, we're checking every single time we have an x value. So now the second argument. I'm going to do the work just to show you, but we already know that x equals negative 5 is inadmissible, but let's do the work anyways. So negative 5 minus 3 is greater than 0. Well, negative 8 is not greater than 0. Again, for the second time, we get x equals negative 5 is inadmissible. Okay, and then we're going to do 5 minus 3 is greater than 0, so 2 is greater than 0. That works. Okay, so our solution is x equals 5.